In this video, I'm going to keep on talking about the Routh-Hurwitz Criterion, which is used to check the stability of a control system without computing the pose of the closed-loop transfer function. So to check the stability of a control system, so the general approach is to check the pose of the closed-loop transfer function to make sure the poles are in the open left half plane. Now, because for the general control system, the pose of closed-loop transfer function can be difficult to compute. So, one of the approaches that have been developed so far, a very popular one, is called Routh-Hurwitz Criterion. Okay, so here I'm going to give a recap of what is the general idea of the Routh-Hurwitz Criterion, especially how to compute a Routh array. Okay, and then what conditions are used to verify if a control system is stable or not. Okay, let's say I've given a control system given by use of given the input use of s and output y of s, and the transfer function g of s is given by this is 2 times s squared plus 2s plus 25, and then divided by s to the fifth plus s to the fourth plus 3s cubed plus 9s squared plus 16s plus 10. So that's my closed loop transfer function. So to use the Routh-Hurwitz criteria to check if the system is stable or not, we have to compute a Routh array. So the Routh array is computed by, first of all, you put the horizontal line, the vertical line, and then you put all the bottom, this left hand side. Okay, here what we put here is s to the power, some power. So basically, what we have is we have s to the highest power, s to the fifth, s to the fourth, s to the 3, s to the square, s to the 1, s to the 0. So the maximum power of this s to the fifth is determined by the degree of my transfer function over here. So this is to the s fifth. The maximum power is to the s fifth. So here I also have the maximum power started with s to the fifth. Then I reduce that. This is what you put over here. Once we do that, so we have to put all the numbers for different rows. So for the first row, as I mentioned in the previous video, so it's just we just put all those numbers we already have in the defined by the denominator in my transfer function. Okay, so what we do is we put all the numbers. Let's assume the coefficient for the denominator from the highest power of s to the lowest power of s is given by 1, 1, 3, 9, 16, and 10. So we just put it this way. Going 1 and 1, so first two rows, okay. Then start with the very corner of first one, 1, then go down 1, then go to the right 3 and 9, then 16 and 10. Of course, you can also put a 0, 0 if needed, okay. So once we do that, we can also compute all the other than the first two rows, all other rows should be computed based on the rules I mentioned here. The rule is every number I compute over here is to compute it by first I figure out what is the entry right above it. Then we apply the rule. What do we call it? In the previous video, you can check the previous video. It's called cross back. So the cross means the product. Back, the first back means is minus. Cross again means the product. And this last back means is divided by. Okay, so 1 cross 3. Okay, cross minus 1 cross 9 and divide by 1. Okay, that's what we have for the red one. Okay, so it's 1 cross 3 minus 1 cross 9 divided by 1. So that's negative 6. Okay. We can also compute this, follow the same rule for the blue one over here. Let's see. Let's do the blue one over here. So the blue one is given by, first of all, figure out what is right above it. So we'll start from there. It's 9. Okay. Then we do cross back. So it's 9 times 16 minus 3 times 10 and divide by 9. Okay, that's what we have. So by doing some simplification, we get this number over here is 38 divided by 3. The last one over here is we do the same thing. So the purple one. So we find an entry right above it, which is 10. So after we start from here, we use the rule cross back. So cross, okay, is 10 times 0 minus 16 times 0 divided by 10. So it's still 0. Of course, we can compute all the numbers for the next row, so on and so forth. Then we check the first. This is the entire numbers we computed over here. That are right using the green color is that's called a Routh array. Okay, And we don't have to check the complete the entire Routh array. What we need to check is first column of the Routh array change sign or not. If it's yes, if it changes sign, not stable. If it's no, doesn't change sign, it's stable. And also the number of, okay, right, emphasize it, the number of change in sign is also equal to the number of poles on the right half plane. Okay, so that's also another part we can see. So generally speaking, if you only check the stability of the system, we only have to check if the first column the Routh array changes sign or not. So I don't have to compute all the rows as long as I figure this negative number C, because I already see the first row here 101 is already doesn't change sign, okay, but from 1 to negative 6 changes sign, so it's not stable, okay, because it's changed sign, so not stable. Okay, so the next question is, what is the application of the stability of a control of stability of stability analysis? Okay, let me rewrite stability analysis. Like, okay, it looks like the Routh array or like Routh-Hurwitz Criterion is very good. So what can we use it? So in what cases can we use it? Okay, so one of the important application for using the check the stability is if we have some variables, unknown variable in the control system, we want to verify, we want to find out the range of that parameter or the variable, and we can use to ensure stability, and then we can use a Routh-Hurwitz criteria to actually get a number of like the inequalities, and which will determine the range of those parameters. Okay. Here I'll give you a very simple example talking about how we could use the Routh-Hurwitz criteria to determine the control system parameter. Okay. So for example, here I give a very simple control system, which is a unit negative feedback, and K here you can consider this as a control, and the system given by 1 over s plus 1 times s plus 2. So that's my system, and this is my control, and this is given certain input output. So you want to make sure that I select K such that the system is stable. Okay. So the question is identify the range of control gain K such that the feedback control system is stable. Here I assume of course this K is positive. Okay. So first of all, to do that, we first need to compute the closed loop, the transfer function basically, right? The closed loop, the transfer function. So the transfer function, because this is we can use a block diagram to compute the transfer function. So this is a cascade, and also the unit negative feedback. Okay. So the transfer function is given by the cascade is just this guy times this guy. So it's just K divided by the whole thing. If you time 1, just move the K to the numerator. So K times s plus divided by s plus 1 times s plus 2, and divide by 1 plus, because the negative unit feedback is 1 plus K divided by s plus 1 s plus 2. Okay, so if we multiply both the numerator and denominator by s plus 1 s plus 2, so we'll cancel out all these denominators on the numerator and denominator. So we end up getting here is K divided by s times s plus 1 s plus 2 plus K. All right, if we have to, because we have to write this form as sort of like this to the different power of s, we cannot write it as the product. So what we do is, let's go back here. So we write this as K divided by s cubed plus 3s squared plus 2s plus K. So that's what we have for the transfer function. Now to ensure stability, we have to make sure the poles of the transfer function must in the open left half plane. In other words, if I check the Routh array, the first column should not change sign. Okay, now of course here I have some parameter K over here. So I follow the same procedure I mentioned before. So first I build a Routh array. Okay, the Routh array is I use a horizontal vertical line over here, and on the right above, on the left hand side of the horizontal line, I put an s to the cube. This is the highest power I have. S squared reduced by 1, s1, s0. Okay. Then the number I have parameters of coefficients is 1, 3, and 2, and a K. Okay, so I put here 1, 3, 2, and a K. Of course, I put 0, 0, since I need it later on. Okay. So then we compute use the same principle I mentioned in the previous page. What I do is, in order to compute this number, so what I do is I find this one right above it, which is 3, uses the rule I mentioned, cross back, cross back. So 3 times cross 2 is 3 times 2, back is minus 1 cross k is 1 times k, and divide by 3, back is divided by 3. So this entry is 3 minus k divided by 6 minus k divided by 3. This one, to compute this entry, I use the same rule. First find the entry right above it, which is k. Use the cross back, so it's k cross 0 times 0 is 0, minus 2 times 0 is still 0, and divide by k is still 0 over here. So this entry, I use the same rule. Okay, it's a cross back. Okay, so it's a 2 minus k times 3, I put it over here, time 2 minus k divided by 3 times k, minus 3 times 0, divide by 6 minus k divided by 3. So this one just give me k over here. So our computer finishes the Routh array. Okay, so what I want to check is make sure that once I select k, the first column of my Routh array does not change sign. So let me check the first column of my Routh array. The first column given by 1, 3, 6 minus k divided by 3, and k. Because this is 1 and 3, they are already positive. So which means if I don't want to change the sign, I want to make sure that 6 minus k divided by 3 is positive, and also my k is positive. That'll be fine. Then it does not change the sign. The first column does not change. So to make sure that 6 minus k divided by 3 is positive, so k must be less than 6. Of course, k has to be positive to make sure that it doesn't change the sign for last entry, which means that k has to be between 0 and 6 to make sure the system is stable. Okay, so this is a general principle we use for the Routh-Hurwitz Criterion. So the first rule for the Routh-Hurwitz Criterion says all the coefficients of my denominator must have the same sign. The second rule says I have to compute the Routh array and try to figure out some algebraic algebraic operation such that the first column of this array should not change sign. So that's the first rule. Two general rules. There are also some special cases of the Routh-Hurwitz Criterion, which is the first, especially for the when we compute a Routh array, it may make the computation invalid. For example, if something divided by 0, we don't know what we should do. Okay, so there are a couple of special cases of the Routh-Hurwitz Criterion. So I'll talk about it in the next part of this video. So the first case is if there's a 0 in the first column of the Routh array, but other elements of the row containing 0 in the first column are non-zero. Okay, I'm going to give an example showing what I mean by that, because it's really a little bit complicated, but let me explain what this means. For example, if I give you the use of S, the closed loop transfer function for a given control system given by G sub S. So G sub S is 1 over S to the 5th plus 2S to the 4th plus 2S to the cube plus 4S squared plus 11S plus 10. So first of all, if you look at the coefficients, so of course I can make it as complete as 1. This coefficient is 1, 2, 2, 4, 11, 10. Yeah, they are all positive. Okay. So we cannot say concrete about stability by only check the sign of the coefficients. Okay, we should keep on going. We should check the Routh array. All right. Okay. Now let's build a Routh array. If I build a Routh array, what's happening over here is I have so the highest power S to the 5th. So I build a vertical horizontal line and vertical line. For the vertical line, I have S to the 5th, S to the 4th, S to the 3th, until S to the 0. Okay, that's simple. Then I put all the numbers in. So I have 1, 2, 2 and 4, 11. This one has to be 10. Okay, 10, right? I put also 0 over here. Okay, 10 over here. So 11, 10. Okay. So unfortunately, if we follow the rule that I mentioned to compute the first entry over here, so I have look at this number. So I have check the number right above it, which is 2 over here. I do cross back. So this number should be computed as 2 times 2. That's 2 cross 2 minus 1 times 4 and divide by 2. Okay, back is 2. So this is giving me 0. So this is 0, okay? We can keep on computing. This is this number, okay, this number over here is, this number here, how I compute it is, you find the number right above it is 4. 4 times 11 minus 2 times 10 divided by 4. So it's a cross back, okay? So it's 44 minus 20, so it's 24. 24 divided by 4 is 6, okay? So this one use the same rule, cross back. So 10 minus the 10 times 0 is 0, minus 11 times 0 is also 0, and divided by 10 is still 0 over here. Now there's a problem over here because this is 0. You want to compute this number right over here. I already give you a number over here, of course, but before you do that, if I use the same principle I mentioned, so this number, over here is calculated as, originally is calculated as, find a number right above it, so it's 0 times cross 4 minus 2 cross 6 divided by 0. So this is the problem. It's divided by 0. Now we don't know what's the actual value it is. So what we do over here is, the principle is, we here, for if there's a number over here, of course those are the we have non-zeros over here, okay? So what do we do over here, if it's not all 0, it's just one, this first entry is 0, this is not 0, what do? We replace 0 by a small, I want to emphasize here is a positive epsilon, okay, by this one, which is approaches 0 after computing the rate. So first of all, we assume we have something is some positive, small positive epsilon, and then we finish all the calculation. After finish all the calculation, we let this epsilon approach positive 0, approach 0 from the positive side to see what's happening. Okay. So here I replace by epsilon. Okay, very small one over here. So I follow the same principle I mentioned. You just replace by epsilon. What happens here is this become epsilon, this one became epsilon. Okay, so that's why we have 4 epsilon minus 12 divided by epsilon. Okay, I don't want to compute do all the calculation over here. To do all the same calculation, you follow the same principle. What you have is you can compute a raster array like this. Okay, so once we do that, we have to check if the first column of the raster array changes sign or not by letting, here I emphasize over here, epsilon goes to 0 plus. Okay, so it's if I draw it over here, let's say this is 0. Let's say for example, this is epsilon. So this is you get 0. So this is, let's say this is 0 point. You are almost very close to this point, but you're not reaching the point. It's still positive, basically. Okay. All right. So if we do that, so the first column is given by 1, 2 epsilon, 4 epsilon minus 12 divided by epsilon, 6 minus 10 epsilon squared divided by 4 epsilon minus 12 and 10. Okay. So if it checks the numbers of the sign, so 1 of course is positive, 2 is also positive. Epsilon, yeah, like I said, epsilon goes to 0 plus. It's still positive, so it's positive. This guy, so 4 times epsilon, this is a pretty small, although it's positive. You minus 12, of course, is negative, right? And divide by epsilon also positive. So negative divided by positive is still negative. So this has become negative. So I don't have to check all those later on because this is already changed sign. So it's not stable. Okay. So this is the first special case. The second special case is there is a 0 in the first column, and other elements of the row containing the 0 are also 0. Okay, this is a little bit special case than what I mentioned before. I'm going to do it here, make it a little bit clear. There is. Okay, so let me give you an example showing what's happening. For example, if I give you a transfer function, the closed loop transfer function g sub s is given by this. Okay, it's given by 1 over s to the cubed plus 2s squared plus 4s plus 8. Okay. So if I compute the raster array, okay, so I put all this highest power s to the cube s squared. So I put this horizontal line and vertical line, and I put the s cube, s squared, s1, s0 over here. So I throw in some numbers, put all the numbers in. I have 1, 2, 4, 8. It's a 1, 2, 4, and 8. So I can put 0, 0 if I need it. Okay. If you compute that one, it follows the rule. So if you compute this number is given by, you find the number right above it is 2, right? 2 cross is 4, minus 1 cross 8, and divide by 2, this is 0, okay? Similarly, if I compute this number over here, So this is 8, right about it, 8 times 0, 8 cross times 0, minus 4 times 0, cross 0, and divide by 8. I still have 0. You have entire row is 0. Okay? So this one, we don't have to continue doing everything. So this is automatically unstable. Okay, so if you look at the pole, what happened over here, this is representing 1 over s plus 2 times s plus j2 and s minus j2. So this you have j, of course j is square root negative 1. So you have poles on the imaginary axis. You don't have, it's not a, typically it's not a stable, not called stable. Okay, so that's about the special cases that I talk about. So generally speaking, the last case is what I mentioned over here is called stable. If you find one entire row after you compute the Routh rate 0, you don't have to keep on computing. You just say this is unstable. If you have only the one entry, the first column, one column of the first entry is this is 0, but the entire row is not not complete 0. You still have non-zero entries over there. What you do is you replace the this one by epsilon, and then you check with your first column. Let your first and epsilon, and if you finish all the computation, and then you after compute all the numbers, and you check for the first column. You check if the first column changes sign by letting this epsilon goes to 0 plus, which means it's still positive, but it's very close to infinitely small. Okay, so that's about the Routh-Hurwitz criterion.